Thanks for coming. Welcome to the Working with WorkManager session. My name is Sumir Kataria. I'm a software engineer at Google.
Hi, my name is Rahul Ravikumar. I'm also a software engineer at Google.
And we both work on Android architecture components, particularly WorkManager. Let me grab my... All right, so what are we going to talk about today? We're going to give you a State of the Union about WorkManager. It was released at Google I/O. I want to give you an abbreviated guide to WorkManager. So for those of you who haven't used WorkManager before, we want to go over some of the basic APIs. And we're going to spend the most of the time talking about WorkManager, the questions you've asked, things that have been frequently misunderstood, and also the new changes that we've made since I/O. So let's start with the State of the Union. There have been 11 releases of WorkManager since Google I/O. And these are alpha releases. Today was the 11th one. And beta is coming soon. So those of you who watched the keynote yesterday may have heard that beta is coming this month. This was news to us, too, but it's coming this month. We were very close, but I guess we're doing it this month now. So we want to give you an abbreviated guide to WorkManager. And what is it, for those of you who are just completely new to this? It's a library for managing deferrable background work. It wraps Job Scheduler and Alarm Manager broadcast receivers. It's backwards compatible to API 14. And those of you who've used Job Scheduler will find many of the concepts very familiar. So let's talk about work. You've got a unit of background work, and we'll talk a little bit more about how we create it and how we enqueue it later. But you've got it, and how does WorkManager execute this work? This is a graph that might help you. While your process is up and running, we'll feed it to this executor that we have that does the work. It could be a thread pool. You can customize this thing. But your process may be killed, and WorkManager is guaranteed to do work. It may defer it, but it will do that work when the constraints for that work are met. So we also enqueue it in the background. So if you're API 23+, we use Job Scheduler. And before that, we use an Alarm Manager and broadcast receiver implementation. So whenever the signals are met, let's say that you've put in some work for a 2-hour time delay when you have network, when all of those conditions are met, it'll still go to the same executor.
All right. Let's do a quick API walkthrough for those who have not seen the API. So the fundamental unit of work in WorkManager is a worker. Here I'm defining a calculation worker. It extends the worker type. So now the only thing that you need to do when you define a new worker is to extend doWork. doWork returns a result. Here I'm returning a success. You can also return a retry or a fail. I'm doing some expensive calculation on a background thread. So you don't have to worry about threading here, because WorkManager is guaranteed to schedule your work on a background thread. And here I'm returning a result.success synchronously. So that's it. I'm pretty much good to go. So now you've defined a worker. How do you actually make that work run? So for that, you need to enqueue a work request. So there are two types of work requests. One's a one-time, and the other one's a periodic work request. Here I'm using a one-time work request builder. And I'm building it with the calculation worker that I just defined in the previous slide. So I'm setting an initial delay, and this is a timing-based constraint. And this tells WorkManager to only run the work after 2 hours have passed since the point of enqueue. I'm also setting another constraint, which is the charging constraint. This tells WorkManager that this work is only eligible to run when the device is actually connected to our charging, when the device is actually charging. I add a tag. I'll talk about tags in more detail, and I'm finally calling .build. Now, all I need to do is to call getInstance and enqueue the work, and that's it. Now the work is scheduled. So now you've scheduled your work. You've defined a bunch of constraints. And it's hard to keep track of. And if you want to keep track of what state your work is in, then you want to call getWorkInfo by ID live data. And this returns a live data of a list of live data of a work info. And so workinfo is the type that determines the state of your work. And live data here is a lifecycle-aware observable. So once you attach it to a lifecycle owner and you define an observer, you can observe the state transitions of the work request. So it'll go something like, once you enqueue the work, it'll go into enqueued. Once the constraints are met, it'll go into a running. And then finally, because you return success, it'll go into the succeeded state. So Remember that tag that we added when we built the one-time work request? You can also get work infos by tag, live data. And tag is something that you associate with a work request. And there can be one-to-many. So you can associate the same tag to multiple work requests. And here, I'm calling get work infos by tag live data. It returns a live data again. Notice how it returns a list of work info and not a single work info. And again, I can do the same things that I did in the previous slide. So one of the coolest features of WorkManager is the ability to chain work. So that helps you define an acyclic graph of work. And here I'm asking WorkManager to begin with A, B, and C. And here, A, B, and C are work requests. And I'm saying that D and E are only eligible to run once all A, B, and C are done. And when I use the begin with API, I'm asking WorkManager to run A, B, and C potentially in parallel. Whether they actually run in parallel is determined by the capabilities of the device and the size of your thread pool. And finally, I'm calling a then on F, G, and H. Again, that now F, G, and H will only run once all the preceding works are done. Finally, don't forget to call enqueue. That's when all the magic happens. So now you called enqueue. Now you might be wondering what begin with returns. So begin with actually returns an instance of work continuation. And a work continuation is a node in your acyclic graph. And this lends to a very fluent API. So every time you call begin with, it returns a new continuation. And every time you call .then, it returns a new instance of another continuation. Finally, don't forget to call enqueue. The one important thing that you need to remember is when you chain work, the outputs of parent or the outputs of the parent work request become inputs to your descending work requests or your children. This helps you manage state and send state from the parent work to the descendant work. And so now, finally, WorkManager also exposes the APIs to cancel work. So for some reason, if you want to do that, you can cancel work by ID. And every work request has a unique ID. So here, we are canceling work by that ID. And we can also cancel all work by tag. So those are the two APIs. And that's it.
And I want to point out that all the APIs we've been showing are for Alpha 11. So you may notice some slight changes for those of you who have been using this API before. But everything is live today. So let's talk a little bit about how you can get the most out of WorkManager. And these also include questions like, how do I do a certain type of task? Why does this work this way, a certain way? And the biggest one that we get a question about is threading. How does threading work in WorkManager? So we talked about a work request. Rahul just mentioned that. And you enqueue it. What happens to it then? So we have an internal, we call it an internal task executor. You can think of it as a single-threaded executor. And the enqueue goes to that, which stores it in a local database. So every app that uses WorkManager has a WorkManager database. This is the source of truth. This is where we keep track of the state of your work, your inputs and outputs, everything. With the dependency chains, everything goes in this database. So after it's been enqueued, sometime later, your constraints are met. And the OS tells you that. If you have no constraints, it's eligible to run it right away. If there are constraints, the OS will tell you, oh, you have network, you are charging right now, whatever it is. Same task executor uses a worker factory to create a worker. Worker factory is exactly what it is. It's a factory for workers. And you can make your own. You can customize and do things with that. We'll talk more about that later. After the worker's been created, we execute it on an executor. And this is also a thing that you can actually customize. We'll talk more about that later as well. But what if you don't want to execute something on that executor? We give you a default one. You can specify your own, but what if you're using RxJava? What if you're using coroutines? What if you have your own bespoke solution that you want to use to run things in the background? This was a request that came up quite a lot when we first released WorkManager. So to do this, we want to provide you an API to let you do work on your own and just tell us when it's done. So you want to signal async work completion to us. And for that, we use a class called Listenable Future. Those of you who use Guava will be very familiar with this. But we split it out, and the Guava team has helped us with this, so everybody's collaboratively worked on splitting this out to its own lightweight artifact, so you don't need a full Guava dependency for this. It's literally one or two classes now. And it's a feature that can have one or more listeners, and those listeners can be invoked on a specified executor. That's all it is. It's very simple. So using this listenable feature, we made a class called Listenable Worker, which only has one method that you need to override. It's called startWork. We'll call startWork on the main thread for you. You give us back a listenable feature. You do whatever work you want on whatever thread you want, and when you're done, just set the result on the future, and we'll be able to listen for it, and we'll be able to react to it. So the actual threading model in WorkManager is, after your constraints are met, it goes to the task executor, which uses the worker factory to create a listenable worker. We call startWork on it, and we also attach a listener so we can listen to whenever you're done. What this means is that the worker class, which is still around, is a simple listenable worker. So we've got the doWork method that we talked about. We override the startWork for you. We create a future. On that background executor that I talked about, the one we provide by default, we execute the work. And we, of course, return the future. So now we have two classes, worker and listenable worker. What's the differences between them? Workers, we consider those a simple class. For most use cases, we think that's sufficient, is a class that runs synchronously and on a pre-specified background thread. Listenable worker runs asynchronously on an unspecified background thread. So worker.doWork is a synchronous API. You're expected to finish what you're doing there. If you're trying to create a listenable worker, you may need to return a listenable future, which is an interface. If you have access to Guava, you have access to many kinds of listenable futures. If you don't have access to Guava or don't want to add the dependency, resolvable future is a lightweight implementation that we provide in Android X concurrent futures. So you can use that. So let's look at an example. One of the things that a lot of people are trying and doing incorrectly with workers is that they're trying to get locations. And we're going to specifically use the fused location provider client. So if you listened to the Kotlin suspenders talk yesterday, they also use this. It's a GMS core API to asynchronously get your location. Remember that a worker class is synchronous. So if you attach a callback and later get informed about it, but return success, your work is already completed. It's not going to work the way you think it is. So first thing we do here, we're using a listenable worker, is we create a resolvable future. So this is the future that we'll return and do all our bookkeeping on. In the startWork method, we'll check to see if we have permissions. If we don't, we'll set a failure on the future. Otherwise, what we'll do is we'll get that fused location provider's last location. This is kind of like a future in GMS core or Google Play Services world. And we'll call this getLocation method, which I'll go into, and then we return the future. So that's sort of the high-level startWork. In the getLocation method, we'll use that task, and we'll add a listener to it. If the task is successful, we'll pass that location back with a success status. Otherwise, we'll set an exception on the future. So that's it. We've basically addressed like the three cases where we want to have a successful or an unsuccessful task, or if we don't have permissions. And WorkManager will attach that listener. It'll listen to the success or failure of your task and do the bookkeeping as necessary.
All right. Let's talk about operations. Now, remember, Sumir mentioned that WorkManager uses a database as a source of truth. So anytime you enqueue or you cancel work, we have to do some bookkeeping, and we have to make sure we keep track of what your intentions were. So these involve writes to a database, and because there are writes to a database, we have to do them on a background thread. So as a result, they're asynchronous. What if you actually wanted to do something after the enqueue happened or the cancel happened? So you want to make sure that those operations completed before you want to do some more stuff. So for that, we've introduced a new API. So now enqueue and cancel actually return a new type called operation. Operation is a very simple interface. It has two methods. So it has a getState API, which returns a live data of an operation.state. If you attach an observer to this live data, you will see that the operation transitions from an in progress to a successful or a failure. You can also call getResult, and this returns the familiar listenable feature type. And remember that this API will only return the terminal state of the operation. It won't give you the intermediate states. So If you're attaching a listener, you will only ever get a success or a failed, and with the exception if telling you why the failure happened.
Another question a lot of people have is, when is work stopped? What happens when you stop work on behalf of WorkManager? Oops. All right. So there's 3 cases when work is stopped. The first is very simple. Your constraints are no longer met. So you said, for example, that I need a network to do this upload task, but your network got lost. So we will stop your work at that point. A second case is that the OS preempted your work for some reason. For example, you exceeded the 10-minute time limit that the OS gives you to do your work. Or the device decided to go into doze mode for battery savings or something like that. And the third reason is that you just canceled your work somewhere else in your app. How do we stop work? There's a method, Listenable Worker on stopped. We call this method when we stop, so just override this and you get your stop signal right there. We also cancel that future that we talked about, so you can also just add your own listener and look for that. So this is when one of these 2 things happens for you, whichever one you're looking at, this is your signal to be a good citizen and clean up. Because after this is called, the process may be killed by the OS. So if the OS woke up your app's process just to run this work, it could actually kill it when it decides that the work should stop. And if you happen to return something after this signal, say you returned a success, we ignore it, because as far as we're concerned, your work has been stopped. Whatever you're doing is no longer necessary to be done. You can also poll for stoppages in your worker, so you can also call the isStopped method, and that'll tell you whether you've been signaled for stopping. So let's look at how you can be a good citizen and clean up. So let's say in this example, we're parsing a file asynchronously. Let's say it's a huge file, so you're doing it in a worker. And you've got that familiar resolvable future thing that I showed you earlier. You've also got this input stream, so you're reading a file. Right? So in start work, you say parse file. This is doing something asynchronously, and you return the future. Here's parse file. So you've got some executor or whatever, a coroutine, it doesn't matter. You're asynchronously doing that runnable that follows. So the first thing you might be doing is you're opening the file, you're reading each byte out of the file, doing something with that byte, and then when you're done, you set a success because you're done. And then you have the necessary try-catch finally after that, so that you can clean up after yourself. So how do we handle when your work gets stopped while this is executing? So like I said, we override the onStop method. Let's say that we want to just finish what we're doing. We could easily just close that input file stream. OK, so what happens now? You've done that. Let's go back to the code. Well, if you're in the middle of that read loop, and you close a file, it throws an exception, right? Next time you try to read something. Well, fortunately, you're already handling that exception right there. So it looks like you're good, right? You're done. Or are you? There's one more case that you forgot about here, which is that what if the onStop happens before you even open the file? So now you're no longer looking for that stop thing because you never got that signal. You'll read that file because it opened after you tried to close it, which it didn't do anything for. So you'll do all of this work. And how you fix it is use that isStop method. So basically, while you're in that loop, you can always just make sure that you're looking for stoppages. So this is a good example of how you would honor the OS's signal to you or WorkManager's signal to you that you should stop and be a good citizen.
Right. So every time you enqueue a method, every time you enqueue a work request, the work request goes through several state transitions. And I'll talk about how they look. So let's look at the life of a one-time work request. So when you enqueue a new work request, it can end up in one of 2 states. It can be blocked, if it's blocked on another work request, given it's a chained work, or it can be enqueued. Once the constraints are met, it goes into running. And this is the point at which the worker is being actively executed. Once, depending on the result that you return, on how you signal work completion, we'll take it to one of the terminal states. So if the worker returns success, then it's we'll terminate it with a succeeded state. If the worker returns a failure, then we'll mark it as a failure, and that also is a terminal state. At any point in time, while the worker was in a non-terminating state, if you call cancel, then if you actually retry, then we'll apply the back-off policy, and then we'll retry. So the worker will go back to the enqueued state. At any point in time, if you have a non-terminating state and you call cancel, it'll end up in canceled. So this is what a life of a one-time work request looks like. Now let's look at periodic work. Periodic work is almost the same. Because periodic work can't be chained, there is no blocked state. So it always ends up in the enqueued state. Once the constraints are met, it'll go into running. So whether you succeed or you retry, it'll go back into the enqueued state. Now, this might seem confusing. If you succeed, then the work really isn't done because it's a periodic work. We'll just wait for the next interval. If you fail and you ask us to retry, then we'll apply the appropriate back-off policy, and then we'll increment the run attempt count. So we'll tell you that this is the second time that you're trying to run it for that last period. And if you mark your work as failed, then we'll transition it to the failed state. At that point, your periodic work won't run again. And again, anytime your work is in a non-terminal state, and if you ask us to cancel it, we'll mark it canceled. So let's apply those rules to how life of a chain of work looks like. So here, A is the parent of all workers. So when you enqueue this chain of work, only A is in the enqueued state, and all descendants of A are actually blocked now, right? So let's assume A's constraints are met, and it goes into the running state. Once A is done, let's assume it succeeded. So it unblocks B and C now. So B and C now become unqueued, and then they go into running. And for the sake of the argument, let's assume that B succeeds and C fails. What happens now? Because B succeeded, it unblocks D. So D goes into the enqueued state. But notice what happened to E, F, and G. They all failed. So the key takeaway is that if a unit of work fails, then all descendant work is also marked as failed. If a unit of work is canceled, then all of its descendants are also marked canceled.
So I want to talk about something called unique work. And let's start with the little question here. What's wrong with this code? So you've got an application object in the onCreate. You're enqueuing some periodic work. The problem here, and I've seen this in a few bugs, is that this enqueues periodic work every time your app process starts. And that's probably not what you're trying to do. You're trying to set up a sync here. Let's say it's syncing your data every day. If you call this code every time the app starts, every time you've got another thing that's syncing your code, you really only want one of them. So unique work basically is something that lets you specify conflict policies for a database insert. Think of it like that. Like if you insert the same key into a database again, what do you want to happen? Do you want to overwrite what's already in there? You want to ignore what you're trying to do? That's what unique work does. It basically is a conflict policy for WorkManager. And here's the syntax for it. It's pretty simple. Unique name is that key. It's that something that uniquely identifies that chain of work. Policy is the existing work policy, or what we call the conflict policies. And then you obviously have your requests. So the existing work policies are the interesting things. There's 3 of them. The first one is keep, which is it keeps the existing unfinished work. So if you have things that are in blocked, running, or enqueued, it will keep them. And if the work is already finished or it's not there to begin with, it'll enqueue whatever you just sent along with that call. The next one is replace. It always replaces the work request in the database. If your work is running, it'll get stopped, as I described a few minutes earlier. It cancels the old work, and it stops it. That's what it does. Append is kind of a special one. It basically appends to that chain of work. So for example, this is useful if you're trying to do something in order. For example, you're trying to build a messaging app, and you're sending messages in order. So you may have a unique chain of work for sending messages, and you want to append new messages to the end of it. So it's basically creating a tree for you.
Right. Remember, Sumir mentioned that in one of his previous slides on how one can customize WorkManager. So let's look at all the things that you can do. So you can actually specify a worker factory that can be used to instantiate your workers and listenable workers. And this is especially useful in the context of dependency injection. So if you're using Dagger and you want to inject something into your worker before the worker starts, this is a good place to do that. You can also specify the default executor that you want all workers to use. You can specify the logging verbosity if you want, if you want to distinguish between a build and a release build, and you want to make sure you log more information to diagnose your problems. And then you can also specify various other job scheduler parameters, like number of jobs that you want us to send to job scheduler, the IDs of jobs that you want us to use, in case you're already using job scheduler before. So if you want to customize WorkManager, then you have to disable the default WorkManager initializer first. So for that, you have to add this entry to your manifest, and note the tools node remove. That means you're removing this. You don't want this entry to get merged. So now that you've disabled the default WorkManager initializer, the next step is to actually create a new instance of configuration. So here, I'm using the configuration builder, and I'm overriding it to specify my own custom executor. So now that I've done that, I can just call workmanager.initialize. I specify the application context and the configuration, and I'm done. So make sure you do this in your application on create or a content provider on create, because the system, the operating system, can actually invoke job services on your behalf. And when job services are being invoked, WorkManager needs to be initialized.
Finally, the last thing we want to talk about before we wrap up is some tips for all the library developers out there. If you're using WorkManager in your library, you have some special use cases that we want to think about. So the general advice we give for library developers is, because WorkManager is a singleton and the application initializes it, as Rahul just showed you, you are not really in control of what's there. Rely on the defaults. So use the default worker factory. The default worker factory that we provide it creates workers and listenable workers using reflection. Rely on that, because you don't know what else is happening. If you need some particular dependency injection or anything else of that sort, you'll have to have a contract with the app. Silo your work with tags. So Rahul also showed you how to tag your work. If you silo all your work, meaning you prefix or put your prefix or your package name or your library name in your tags, you can easily identify all the work that's yours. You don't have to worry about other people's work. You don't have to deal with any of that. You can just get your work and operate on just that if you don't know the IDs. Finally, we do provide the ability for apps to wipe away all work. And this is generally for privacy reasons. This is not something we expect to be called, but it's for that sort of critical use case where you have to wipe user data for some reason. So as a library developer, how do you find out if your work's been wiped or gone from under you? You should look at get last cancel all time millis. It's a very confusing name. OK, next steps. So get WorkManager if you haven't already. And for those of you who have, thank you very much. Your feedback's been invaluable. We're up to Alpha 11. So there's 3 general categories of artifacts here. There's the runtime. There's the KTX stuff, which includes a coroutines worker that we just put in. So you don't have to write your own. And then there's testing support as well. These are some helpful links. Schedule tasks with WorkManager is the developer.android.com section for WorkManager. There's the on YouTube, there's the Google I/O 2018 talk, which talks about all the basics in much greater length. Some of those APIs have changed a little bit, but it's still broadly a good thing to read or to listen to. And also, please file your feedback at our public issue tracker. Beta is coming. We were told that this morning or last morning as well, so we're kind of, we have to get back to work. But thanks a lot. Please visit all the Jetpack libraries on the web, and we'll be outside for any questions that you might have. Thanks.
Thanks.